Planck's constant is a cornerstone of quantum mechanics. It represents the smallest action in our universe. Named after Max Planck, this constant revolutionized physics. He introduced it in 1900 while studying black-body radiation. Planck's constant is fundamental to understanding the quantum world. It bridges energy, frequency, and the behavior of particles. Without it, modern physics would not exist as we know it. To grasp its significance, we must delve into quantum mechanics. This field studies the smallest particles in our universe. Planck's constant is the key to unlocking these mysteries. Let's explore its role and implications further. Planck's constant is symbolized by the letter h. This fundamental constant plays a crucial role in quantum mechanics. Its value is approximately 6.626 times 10 to the power of -34 joule-seconds. This incredibly small number is essential for understanding the quantum world. This tiny number links energy and frequency, forming the basis of quantum theory. It shows that energy comes in discrete packets called quanta, rather than being continuous. The relationship is given by the equation E equals hf, where E represents energy. Here, E is energy, h is Planck's constant, and F is frequency. This equation is fundamental in quantum mechanics. This equation means energy is directly proportional to frequency. As frequency increases, so does energy. Higher frequency leads to higher energy. This concept was groundbreaking and changed our understanding of physics. Before Planck, energy was thought to vary continuously without discrete levels. His discovery showed that energy is quantized, meaning it exists in specific amounts. This was the birth of quantum theory, a revolutionary idea in physics. Let's dive deeper into how this affects particles and the fundamental nature of our universe. Wave-particle duality is a core concept in quantum mechanics. It means particles like electrons exhibit both wave and particle properties. Planck's constant is crucial here. It helps describe the wavelength of particles. Louis de Broglie extended Planck's ideas. He proposed that particles have wavelengths given by lambda equals h over p. Here, lambda is the wavelength, h is Planck's constant, and p is momentum. This equation ties particle behavior to waves. Wave-particle duality explains many quantum phenomena. For instance, electrons can create interference patterns like waves. Yet they also impact screens like particles. Planck's constant is at the heart of this dual behavior. Now let's explore another quantum concept, quantization. Quantization means that certain quantities, like energy, are discrete. They come in set amounts rather than being continuous. Planck's constant introduced this idea. It showed that energy levels in atoms are quantized. In atoms, electrons occupy specific energy levels. They can't exist between these levels. When electrons jump between levels, they absorb or emit energy equal to the difference. This energy is a multiple of Planck's constant times the frequency. This explains atomic spectra. Each element emits or absorbs light at specific frequencies. These correspond to the energy differences between levels. Quantization is fundamental to understanding atomic structure. Now let's look at Planck's law. Section 5, Planck's Law of Black-Body Radiation. This section delves into one of the most fundamental concepts in quantum physics. Black-body radiation refers to the emission of light by a perfect absorber, an idealized physical body that absorbs all incident electromagnetic radiation. Classical physics couldn't explain its spectrum, leading to significant gaps in understanding the nature of light and energy. Max Planck proposed a groundbreaking solution using his constant, which revolutionized the field. He showed that energy is emitted in discrete packets, or quanta, rather than a continuous wave. Planck's law describes the intensity of radiation at different frequencies. It fits observations perfectly, providing a precise mathematical framework. The formula is I of nu t equals 2h nu cubed over c squared divided by e to the power of h nu over kt minus 1. This elegant equation encapsulates the relationship between these variables. Here I is intensity, nu is frequency, T is temperature, h is Planck's constant, c is the speed of light, and k is Boltzmann's constant. Each variable plays a crucial role in the behavior of blackbody radiation. Planck's law resolved the ultraviolet catastrophe, a major issue where classical physics predicted infinite energy at high frequencies. This was a major problem in classical physics, causing significant theoretical challenges. It predicted infinite energy at high frequencies. Planck's quantization avoided this, marking a pivotal moment in scientific history. Let's explore how it impacted physics further, paving the way for the development of quantum mechanics and transforming our understanding of the universe. Section 6. Resolving classical physics issues. Before Planck, classical physics had many limitations. It couldn't explain blackbody radiation or the photoelectric effect. Planck's constant was the key to resolving these issues. It introduced the idea of quantization. The photoelectric effect showed that light ejects electrons from metal surfaces. Classical theory couldn't explain the threshold frequency. Einstein used Planck's constant to solve this. He showed that light comes in quanta called photons. Planck's constant also explained atomic spectra and specific heat capacities. These phenomena were mysteries before quantum theory. Quantization provided a new framework for understanding them. Next, let's look at applications in modern technology. Section 7. Planck's constant and quantum computing. Quantum computing is an exciting field. It uses quantum bits or qubits. Unlike classical bits, qubits can exist in multiple states simultaneously. This is thanks to superposition and entanglement, which rely on Planck's constant. Qubits operate using quantum states. Their behavior is governed by Planck's constant. Quantum computers can solve problems much faster than classical ones. They have potential applications in cryptography, optimization, and simulations. Planck's constant is also crucial for developing quantum sensors. These devices measure physical quantities with extreme precision. They rely on quantum phenomena like tunneling and superposition. Now, let's explore another fundamental principle. Section 8. Heisenberg, uncertainty principle, and Planck's constant. The Heisenberg uncertainty principle is a cornerstone of quantum mechanics. It fundamentally changes how we understand the behavior of particles at the smallest scales. It states that you can't simultaneously know the exact position and momentum of a particle. This is not just a limitation of our measurement tools, but a fundamental property of nature itself. Planck's constant plays a central role in this principle. It is a fundamental constant that appears in many equations in quantum mechanics. The uncertainty is given by dx dp is greater than or equal to h divided by 4pi. This equation quantifies the limits of our knowledge about a particle's position and momentum. Here, dx is the uncertainty in position, dp is the uncertainty in momentum, and h is Planck's constant. This relationship shows that the more precisely we know one quantity, the less precisely we can know the other. This equation shows the limits of measurement precision. It highlights the intrinsic uncertainties that exist in the quantum world. The smaller the Planck's constant, the greater the precision. However, since Planck's constant is a fixed value, it sets a fundamental limit to the precision we can achieve. This principle has profound implications. It challenges our classical intuitions and forces us to rethink how we understand the universe at a fundamental level. It means that at a quantum level, there's a fundamental limit to our knowledge. No matter how advanced our technology becomes, we cannot surpass this limit. This uncertainty is not due to measurement errors, but is intrinsic to nature. It is a built-in feature of the quantum world that we must accept and work with. Next, let's explore real-world applications of Planck's constant. From quantum computing to fundamental physics research, Planck's constant plays a crucial role in many cutting-edge technologies. Section 9. Real-world applications of Planck's constant. Planck's constant has numerous real-world applications. It's essential in technologies like MRI machines and lasers. These devices exploit quantum phenomena. Planck's constant also underpins the development of semiconductors and transistors. In medicine, nuclear magnetic resonance imaging, or MRI, relies on quantum mechanics. It uses the behavior of atomic nuclei in magnetic fields. Planck's constant helps describe these interactions. This enables detailed images of the inside of the body. In electronics, transistors are the building blocks of computers. They operate on principles explained by quantum mechanics. Planck's constant is key to understanding their behavior. Finally, let's conclude with the broader significance of Planck's constant. Section 10. The significance of Planck's constant in modern physics. Planck's constant is more than just a number, it's a gateway to the quantum world. It transformed our understanding of nature. Without it, many modern technologies wouldn't exist. Its discovery marked the beginning of quantum mechanics. Max Planck's work opened new frontiers in physics. It led to the development of quantum theory. This theory explains the behavior of the smallest particles. It also solves problems that classical physics couldn't. Planck's constant remains vital in ongoing research. It helps physicists explore the limits of reality. As we delve deeper into the quantum realm, its importance grows. It's truly the quantum key to understanding our universe.